Hello everyone, welcome to another video. This is a lecture on statistical mechanics. We will continue our statistical mechanics, and we had completed canonical ensemble. Okay, canonical ensemble was done. So now we'll this is over. So today we'll be doing uh, grand canonical ensemble. Okay, grand canonical ensemble. So what is grand canonical ensemble here? Hmm? See here in grand canonical ensemble there is this thing called grand potential. Grand potential. Is it all right? Hmm. Okay. First of all, what is there? What is the grand canonical? In grand canonical ensemble, your mu, v, t are constant. Okay. Mu, v, t are constant. Mu is a what? Chemical potential. That means mu is constant. That means what? Means number of particles are changing are constant. Number of particles are changing. Permeable walls or penetrable walls. Okay. Is it all right? Now, V is a constant also. Volume is constant. Okay, that means these are rigid walls. Then your temperature is constant. Means thermally conducting walls. Thermally or diathermic walls. Okay. Yeah. So these are some of the things about grand canonical ensemble. Okay. There's another thing here. There's right now. It's called density of phase point. Density of phase point. So your density of phase point is rho. Okay. Rho is proportional to e to the power minus alpha nr minus beta es. Okay. Or rho pq. PQ coordinates momentum and is rho qp. Position and momentum coordinates proportional to e to the power minus alpha n. Okay. Qp minus beta mu q. Okay. In place of energy es, I just put mu. In place of nr, I just put n. Okay. Next is your leading thermodynamic variables. Leading thermodynamical variables. See, in grand canonical ensemble, there is a thing called grand potential. Okay, grand potential. There's a thing called grand potential phi. Okay, phi is what? U minus Ts minus mu n. This is your grand potential phi. Okay, phi can also be written as minus kT ln z minus kT ln z, where z is a what? Partition function of force. Okay. So by knowing your phi, we can calculate what other thermodynamic variables. Okay. Hmm. Okay. Let's write some facts about it. Suppose here mu is constant. That means what? I will elaborate a bit. That means it indicates what each member of the ensemble, each member of the ensemble is exchanging number of particles is exchanging number of particles with the surrounding number of particles with the surrounding. Okay, it means it means all members it means all members of ensemble are in contact are in contact with a particle reservoir with a particle reservoir of infinite capacity at chemical potential mean. Infinite capacity of a reservoir means you can give any amount of heat there. Okay. Yeah. Particle reservoir means any amount of particles can go there. Okay. Yeah. So each member of the ensemble is exchanging number of particles in the surrounding, and there is a particle reservoir of infinite capacity. That means whatever particle you give there, it will be constant. Okay. So next, here T is also constant. T is also constant. That means what each member of the each member of the ensemble is exchanging heat with the surrounding. Hence, each member, sorry, each member, each member. Abhay, each member of ensemble. ହଁ ଆମର ଆଜି ରାତି ଆଉ କାଲି ଦିନ ରାତି ଗୁରୁବାର ସକାଳେ ଆସିବ. Hence each member of ensemble is in contact with the heat reservoir. And heat reservoir of infinite heat capacity at temperature T. चल जा रहे हैं. So each member of the ensemble is exchanging heat with the surrounding. Each member of the ensemble is in contact with the heat reservoir infinite heat capacity. Okay. So from the above discussion, you can see it's clear that each member of the ensemble exchange particles and heat with their respective reservoir, right? So before attaining equilibrium, okay, uh, a member of the ensemble like the number of particles and energy can be anything between what 0 to infinity, right? Number of particles and energy can be between 0 to infinity. Hmm. So, the that that a member of ensemble will have nr particles and es energy okay, in grand canonical ensemble is what probability nres is equal to e to the minus alpha nr minus beta es divided by summation ns e to the minus alpha nr minus beta es. One value divided by the total value. Okay, this is for non-degenerate case because there is no g here. If it was degenerate, I would have written g here. Okay, g is for degeneracy, so I would have written a g, but there is no g. For degenerate case, for degenerate case, p n r e s will be what? G is e to the power minus alpha n r minus beta e s divided by summation alpha summation r s g s e to the power minus alpha n r minus beta e s. And this is a what? This is a degenerate. Okay, where g is a what? Degree degeneracy of es level. Is it all? Yeah. Now let's come to grand partition function. Grand partition function. Grand. This is not normal partition function. This is called grand partition function because it belongs to grand canonical ensemble. Okay, Z. Z will be summation rs. You can write it q also, no problem. But let's write it Z only. Gs is over minus alpha nr minus beta es. Is it alright? Okay. Okay. I can write it as, see, there is alpha here. So summation r e to the minus alpha n r. Tell me whether I can write it or not. Summation s gs e to the minus beta s. So wherever there was r, I wrote like this. Wherever there was s, I wrote like this. Okay. So this is actually your partition function in canonical ensemble. If you remember, this is a normal partition function. Okay. So partition function in canonical ensemble. Okay. So this is, let me write it as q here in this case. So z is equal to what? Summation r e to the minus alpha n r q, where q is a partition function in canonical ensemble. Okay. Yeah. Okay. So here e to the power minus alpha, I can write it as um, suppose I will write it as j. Okay. So this is called a what? Fugacity of the system. Okay. System. This is not taken at J, but I have just taken it for my convenience. Because there are too many Z's, Z and Q's. Okay. So I can write it as partition function Z is equal to what? Summation R J to the power NR. Yeah. Into Q. Okay. So this J is a fugacity of the system. The next is what? Internal energy. Internal energy. So internal energy is what, like suppose Z is a what? Summation GS equal minus alpha nr minus beta es. So average energy will be U is equal to minus del by del beta of Z. Sorry, ln Z. No? So minus del by del beta of ln um, ln Z is how much? No need to write Z. No need to calculate here. I'm just writing it. Okay. NR is what? NR is called average occupancy. Okay. Average occupancy. So NR is what? NR is equal to N is equal to minus del by del alpha of ln Z. Okay, average occupancy of the system or average average number of particles in the system. Is it all right? Now, see, in the beginning we wrote that grand potential. In the beginning we wrote grand potential as what? Grand potential phi. Grand potential phi as u minus ts minus mu n, right? This was the grand potential. So d phi is what? D phi is equal to du minus tds minus stt minus mu dn minus nd mu. Okay, this is all right. So we also know TDS is what? TDS is TDS is actually du plus PdV minus mu d. This is also we know, so we can put it here. So put it d phi is equal to du minus du in place of this, okay? Minus PdV plus mu dn minus STT minus mu dn minus nd mu. Okay. So if you see mu d n can be cancelled out. Du cancelled out. So what is left? Minus PdV minus STT minus nd mu. Okay, is it all right? So this is your d phi. Okay. So if you see these three mu v t, these are actually constant in canonical ensemble. So these are here in differentials. Okay. Another way to remember this formula. Okay. Now, number of particles in system can be written as n is equal to number of particles in system. N is equal to n can be written as minus del phi by del mu, and v and t are constants. Pressure can be written as pressure can be written as P is equal to minus del phi by del V mu T. Okay. Entropy can be written as entropy can be written as S is equal to minus del phi by del T mu n. Okay. And so this is your mostly grand canonical ensemble. This is the theory part of grand canonical ensemble. I hope you understood. Okay. Yeah, this is a very small topic, so I hope you understood this topic. We'll do questions from it in the next session, if possible. Okay, okay, that'll be it for this class. We'll see you in the next session. Thank you.